We've looked at distance and displacement and the difference between the vector quantity and the scalar quantity. And now we're going to take a look at speed and velocity, and we're also going to take a look at the concept of acceleration. Speed is defined as the rate of change of distance. Whenever I use the word rate, I mean I'm going to divide by time. So I'm going to take the distance and I'm going to divide it by the time. If I take a look at something called the average speed, I'm looking at the total distance divided by the total time. And then I'm going to see that distance is abbreviated with an S. I don't know why, but it is. And speed is abbreviated with a V. So I'm going to land up with a triangle with S at the top, which is really distance, and V and T at the time. So this is my distance, not my speed. Divide is speed and time. Whenever I use this little triangle over here, I mean that it's a change in. So the change in distance over the change in time. Notice that distance is a scalar quantity and speed is a scalar quantity. So I am not considering direction at all. We measure we measure speed in either meters per second or kilometers per hour. The System International unit for speed is meters per second. So if I have got a car that is traveling 15 kilometers in 5 minutes, and I want to find out what the speed is, the speed will be the total distance divided by the total time. And I can then say it is 15,000 meters divided by 10 times 60 seconds. And we land up with 25 meters per second because I had my distance in meters and my time was in seconds. Let's remind ourselves and convert that into kilometers per hour. So I'm going to land up with 25 meters per 1 second is equal to 0,025 kilometers per 1/3600th of an hour. And I land up with 90 kilometers per hour. During the journey of that particular vehicle, the car might have gone as fast as 110 kilometers per hour, it might have gone as slowly as 70 kilometers per hour. So what I've done is I've looked at an average. Often we want to know what the speed is at an exact moment. So if you had a car speedometer, for example, it would be telling you that moment's speed. So then we need to measure a very short distance and a very short period of time. We call that the instantaneous speed, the speed at that instant. Don't forget that speed is a scalar quantity. Now we're going to look at a concept called velocity. And velocity sounds a lot like speed and looks a lot like speed. It is the rate of change of displacement. Now displacement, you will remember, is a vector quantity. And velocity is therefore also a vector quantity. I take the displacement and I divide it by the time. And you'll notice I've put this little line over here. That means it's the average velocity. And ideally, velocity, I should also put a tiny little arrow above there to symbolize velocity, because then that shows that I'm dealing with the vector quantity. So it's displacement divided by time, but we actually never put them in, but officially one should. And the V above there, the line above the V symbolizes an average. Generally, we measure velocity in meters per second. Again, we could use kilometers per hour, but the SI unit is meters per second. Displacement always has a direction, so the velocity has a direction as well. So we've got 2 minutes. A worm goes at 24 meters at 98 degrees. What is its velocity? Velocity is equal to displacement divided by time. So it's 24 divided by 2 minutes is 2 times 60 seconds. So it's meters per second once again. And I land up with this worm going at 0,2 meters per second, but I've got to give it a direction. It will have the same direction as the displacement at 98 degrees. if I needed to calculate the instantaneous velocity, suddenly I'd need a direction. So this particular situation here, we've got an object, it's moving from the start to the finish, and its average direction would be on a resultant line like that. But at the instant that I've marked here, I draw what's called a tangent to the curve. It is a line that touches the curve at just one point, and I work out the direction of that line in order to determine the direction of the instantaneous velocity. Again, with instantaneous velocity, I land up putting a short distance and a short displacement rather, and a very short time. And I get the direction from a tangent to the curve. Velocity changes as there's a change in speed or direction. So here we've got a person running around a circular track like this. And they land up, they go at exactly a constant speed as they go around. Let's say 10 meters per second. I'm not sure what's going to come out. They're going around 10 meters per second, 10 meters per second, 10 meters per second. But they do not have a constant velocity. Why? Because their direction is changing all of the time. And whenever we consider velocity, we need to have a constant speed and a constant direction. So let's look at this. It's a car, it's not a person. Car travels around a circular track. The circumference of that track is 200 meters. In 20 seconds, assume that the speed stays constant. What is his average speed around the track? So I take the total distance and I divide it by the total time. 200 divided by 20, and I get 10 meters per second. What is his average velocity around the track? Well, if I go once around the track, my displacement is 0. I started at A and I end at A. So it sounds completely useless, and it is, but my velocity is going to be equal to the displacement divided by the time, and that is 0 divided by 20, and I land up with 0 meters per second, and there's no direction to 0. If I had a value, I would have to find a direction as well. What is his average velocity from A to C? I'm going to first need to work out the radius of this circle. So if I have got circumference is equal to 2 pi r, we know that the circumference is equal to 200, and therefore the radius turns out to be 31,83 meters. I need the diameter, which is twice the radius, 2 times 31,83, and that is equal to 63,66 meters. So now, if I'm trying to work out velocity, velocity is equal to displacement divided by time, and the change in displacement from A to C is 2 radiuses, 63,66, and it's only halfway around the track. So if it took me 20 seconds to get around the whole track, it's going to take me 10 seconds to get around half the track. So it's 6,37 meters per second. Wait, in what direction? From A to C, I have a direction that I go towards the west. And finally, what is his instantaneous velocity at A, B, C, and D? So instantaneous velocity is going to be the speed. And remember, his speed was constant. So at A, B, and C, it's 10 meters per second, constantly around the track. But at A, what is the direction? He's moving towards the north. At B, he's moving towards the west. At C, he's moving towards the south, and at D, he's moving towards the east. So for A, it's 10 meters per second north. For B, it's 10 meters per second west. For C, it's 10 meters per second south. And at D, it's 10 meters per second east. An aeroplane is flying in a straight line to its destination 2,200 kilometers away. The pilot wants to maintain an average speed of 550 kilometers per hour. So let's work out how long that should take. So time is equal to displacement divided by velocity, which is going to be 2,200 kilometers divided by 550 kilometers per hour. And I find that this journey should take exactly 4 hours. This is should. That's what should happen. Let's see what does happen. After he has covered 1,100 kilometers, he discovers that his average speed has been 500 kilometers per hour. So let's see what he's achieved in that time, or how long has that taken him. He has gone 1,100 in 500 kilometers per hour, which means that it has taken him already 2,2 hours. How much, so that's already. How much time is he going to need to finish the journey? Well, he has to finish in 4 minus 2,2 hours, which is 1,8 hours. That's all he's got left. How much more distance has he got? His distance left is going to be the total of 2,200 minus 1,100, which means he's still got to cover 1,100 kilometers. So at what speed should he achieve this? Let's read the rest of the question. Determine the speed at which he must proceed in order to finish his flight with his correct average speed and reach his destination on schedule. So I am now trying to work out a velocity. Velocity is displacement divided by time. 1,100 divided by the time he has left, 1,8, and I'm going to find that he now has to travel at the rest of his trip at a speed of 611,11 kilometers per hour.